Welcome to the NPTEL MOOC on Discrete Mathematics. This is the first lecture on set theory. Set theory deals with sets. A set is a collection of objects. In that sense, a set is also an object. Therefore, a set can be a member of another set. When we write A belongs to A, what we mean is that small a is a member of set A. The negation of this statement, which says that A is not a member of A, is written like this. For two sets A and B, we say that A is equal to B if and only if for every x, x belongs to A if and only if x belongs to B. In other words, two sets are equal precisely when they have exactly the same members. This is called the principle of extensionality. Two sets are equal precisely when they have the same extensions. It asserts that sets are defined by their memberships. There is a set with no members. This is the empty set. An empty set is denoted by phi. Note that phi is not the same as the set containing phi. A set with exactly one member is called a singleton set. So here phi is not the same as the singleton containing phi because phi has no member. It's an empty set. The singleton containing phi has one member, namely phi itself. So these two are not the same. If every member of A is a member of B as well, for sets A and B, we say that A is a subset of B. This symbol says A is a subset or equal to B. If A is a subset of B and A is not equal to B, then we say that A is a proper subset of B, and it is denoted like this. Either like this, or sometimes we write like this to indicate that A is a subset of B but A is not equal to B. So these two notations will be used interchangeably. Both mean to say that A is a proper subset of B. Now let us define some operations on sets. The union operation denoted using this symbol is defined like this. X belongs to A union B if and only if X belongs to A or X belongs to B. Another operation is the intersection operation. It is expressed using this symbol. We say that X belongs to A intersection B if and only if X belongs to A and X belongs to B. Notice the correlation between the union symbol and the OR symbol, the intersection symbol and the AND symbol. X belongs to A union B if and only if X belongs to A or X belongs to B. X belongs to A intersection B if and only if X belongs to A and X belongs to B. The third operation is the relative complement. Complement of A with respect to a universal set A is defined like this. X belongs to the complement of A with respect to U if and only if X belongs to U and X does not belong to A. A set A can be deemed a predicate on objects. For example, consider first order predicate or any logical predicate with one free variable. So this statement is essentially a statement about one unknown entity. X is the one unknown entity. For example, it could be a statement of this form, x greater than 5. There is one free variable in this. So you can assume that this is actually a definition of a state. It is talking about all individuals that are greater than 5. We write like this. So using every one variable predicate, we can construct a set. In other words, a set can be equated to a predicate on objects. So let us say we have a universal set U and we deal with subsets of U. And we have these three operations: union, intersection and the relative complement. The algebra defined by these three operations, you can see, is in fact a Boolean algebra, which we have already seen in the module on mathematical logic. Therefore, the following laws hold. By virtue of this algebra being a Boolean algebra, the following laws hold. We have seen the analogues of these laws in the context of propositional calculus. The first one is the identity law. Which says that A intersection U, the universal set, is A, and A union phi is A, which means U is the identity of intersection and the empty set is the identity of union. Then we have domination laws. Domination law says that the universal set U dominates the operation of union. That's because A union U is U for any A, and the empty set dominates the operation of intersection. A intersection phi is phi for any A. Then we have idempotent law, one each for union and intersection. A union A is A and A intersection A is A. Then we have the double negation law, which asserts that the complement of the complement is the original set. U minus A, the relative complement of the relative complement of A is A itself. You can draw a Venn diagram to verify this. If the rectangle represents a universal set U and the circle represents the set A, U minus A is the elements which are outside of the circle. The complement of the elements which are on the outside, the set formed by the elements which are on the outside of the circle will be the elements which are inside the circle. Then commutative loss, it says that both the operations union and intersection are commutative. A union B is the same as B union A, and A intersection B is the same as B intersection A. Then we have associative loss. It says that both the operations union and intersection are associative. You can apply them in any order. When you have a sequence of unions, A union B union C is the same as A union B union C. Therefore, we can avoid the parenthesis and write a sequence of unions in this manner, and this can be extended to any number of sets. Similarly, for intersections as well, A intersection B intersection C is the same as A intersection B intersection C. Then we have distributive loss. It says that intersection distributes over union and union distributes over intersection. A intersection B union C is the same as A intersection B union A intersection C. Similarly, intersection distributes over union as well. A intersection B union C is A intersection B. Similarly, union distributes over intersection as well. A union B intersection C is A union B intersection A union C. You can verify these using Venn diagrams. You would have studied Venn diagrams in school, I am sure. In a Venn diagram, you represent a universal set using a rectangle, and then sets inside can be represented using convex figures, circles typically. So, you have sets A, B, C with possible intersections between them. Then you can talk about A intersection B, B intersection C, etc. A intersection B in this case would be this portion, and B intersection C would be this part. A intersection C would be the common parts between circles A and C. So, using Venn diagrams, you can verify the correctness of all these laws. Then we have De Morgan's laws in this Boolean algebra as well. The corresponding De Morgan's laws would be this: the complement of A union B, let me denote the relative complement in this fashion, is the complement of the relative complement of A intersection the relative complement of B. Similarly, A intersection B complement would be A intersection union, A complement union B complement, where the complement is a relative complement. So, these are the De Morgan's laws of set theory. Then we have absorption laws. Absorption law says that A union A intersection B is A, and A intersection A union B is also A. And finally, we have negation laws. A union, the relative complement of A is the universal set. A intersection, the relative complement of A is the empty set. So, verify all these laws using Venn diagrams or logical arguments. I am leaving it as an exercise to you. The set of all subsets of A is is denoted by 2 power a or sometimes p of a. If a is a finite set, the size of 2 power a, 2 power the size of a. In other words, if a has n members, then the power set of a has 2 power n members. The argument goes like this: if the cardinality of n is a is n, the cardinality of a set is the number of elements in the set when the set is finite. If the cardinality of a is n, then to form a subset of a, for each element of a, we have two choices: pick the element or do not pick the element. Therefore, there are 2 power n ways to form a subset. That is, if x1 through xn are the members of a, for each element either I can pick it or leave it, select it or leave it for each of the n elements. So there are two choices for each element. Therefore, the total number of ways in which you can form the subset is a multiple of n2's, which is 2 power n. Therefore, the number of subsets of A is 2 power n. A set may contain sets so as we have seen, the power set is a set of sets. We define the union of A in this manner. It is a set of all x such that there exists B, where B belongs to A and x belongs to B. In other words, union of A is the set of members of A. If B is a member of A and x happens to be a member of B, then x belongs to union of A. Analogously, we can define intersection of A as x such that for every B, if B belongs to A, then x belongs to B. So, intersection of A is the set of those elements which belong to every member of A. For example, if A is made up of these elements, set A 2, 3, number 4 and the singleton containing just 5, then union of A would be the set of all members of A. Number 4 is not a set, therefore it doesn't have members, but set 2, 3 has 2 members, namely 2 and 3. Set 5 has 1 member, namely 5. So, union of A is 2, 3, 5. Intersection of A is the set of those elements that belong to every member of A. But since 4 is not a set, it doesn't have any member. Therefore, there is no such element. There is no element which is a member of every member of A. An unordered pair is a set of size 2. A set of size 2 xy is an unordered pair. It has exactly 2 elements and there is no particular ordering of the elements. That is, you cannot say this is the first element and this is the second element. These two elements are identical as far as the membership is concerned. So an unordered set is a set of cardinality 2, whereas an ordered pair has two elements x and y, and these elements are to be ordered. You should be able to say that x is the first element here and y is the second element here. So x and y are not symmetrically included here, but an ordered pair can be defined as a set. So let us define the ordered pair xy in this fashion. We define the ordered pair xy as a two element set in which the first element is x itself, whereas the second element is the set containing x and y, the unordered pair. So the ordered pair defined as a set consists of two elements. The first element is an element from the universe, whereas the second element is an unordered pair of the universe, and the first element is a member of the second set. So here x and y are not symmetric. In the sense that x is the first element and it is also a member of the second element, whereas y is only a member of the second element. It does not have an independent membership of the set. Therefore, x and y are holding asymmetric positions within this unordered pair. We use ordered pairs to use what are called relations. A relation is a set of ordered pairs. For a relation R, the domain of R denoted in this fashion is defined in this fashion. X belongs to the domain of R if and only if the x is y, so that xy belongs to R. There is an ordered pair in R where x is the first component. If that is the case, we say that x is in the domain of R. Similarly, the range of R denoted like this is defined in this fashion. We say that x belongs to the range of R if and only if the x is a y, so that the ordered pair yx belongs to R. The union of these two, the domain of R and the range of R, is called the field of R. For two sets A and B, A cross B is the set of all ordered pairs AB, so that A belongs to capital A and B belongs to capital B. That is, A cross B is a set of all ordered pairs AB, so that A comes from the first set A and B comes from the second set, namely B. So if A and B are finite and A has a size of n and B has a size of m, then the cross product of A and B has a size of n into m. That is the number of ways in which you can form ordered pairs with the first component coming from A and the second component coming from B is n into m. Observe that a relation R from A to B is a subset of A cross B. If R is made up of ordered pairs from A and B, then R is a subset of A cross B. A binary relation on A is a subset of A cross A, which is also sometimes written as A squared. An n-ary relation on A is a subset of the cross product of A with itself n times, which is denoted in this fashion, A power n. An ordered pair is also called a two-tuple, and an n-tuple in that sense is defined as an ordered pair consisting of an n minus 1 tuple followed by a single element. For example, when we have elements a1 through an forming an n-tuple, this can be defined as a set in this fashion. Define an ordered pair. First you form an n minus 1 tuple recursively using the first n minus 1 elements, and then include a n in that. So every n tuple can be defined as an ordered pair. And A power n is the set of all n tuples. If xy belongs to R, we write xry. A bit of notation. Now let us define functions. A function f is a relation such that for every x belonging to the domain, there x is a unique y in the range of R, so that xy belongs to f. We will see more about functions in the next class. That is it from this lecture. Hope to see you in the next. Thank you.